In the last video, we saw that the Poisson could be used as an approximation to the binomial if n is large and p is small. And also, never forget it, if n is large and 1 minus p is small. In this video, we're going to look at one or two examples to illustrate that. First, let's suppose that the probability that a person has a particular disease is 0.05. One day, 70 people visit their doctor. What is the probability that fewer than 5 have the disease? Well, let's suppose that x is the number of people with the disease. Then x twiddle binomial 70 0.05. So x comes from a binomial distribution. We find that we have two possible outcomes, either the disease or not having the disease, 70 people, fixed number in the trial, and a fixed probability for each person of 0.05. So it satisfies all the conditions for a binomial. The probability that x is less than 3 is the probability that x is 0, plus the probability that x is 1. That's a rather nasty equal sign, plus the probability that x is 2. We can't use binomial cumulative tables here because 70 is too large. So this is equal to, well, none. In 70, that means that it's 0.95 to the power 70 plus 70c1 times 0.95 to the power 69 times 0.05 plus 70c2 0.95 to the 68 times 0.05 squared. Press the buttons on that, and we get 0.3137, etc., etc., etc. Using a calculator, so we give 0.313 to 3 significant figures. Okay, that is working out what it is using the binomial distribution, which is the correct distribution. But p is small, n is large. We could use a Poisson distribution as an approximation for this. So in part B, we use a suitable approximation to find the probability that fewer than 3 have the disease. Well, the distribution is x twiddle b 70 0.05. The expected mean mu is np is 70 times 0.05, which is 3.5. So if we now approximate with y twiddle p naught 3.5, so we're using a Poisson distribution with mean 3.5 as an approximation. We're looking for the probability that x is less than 3. That will be approximately equal to the probability that y is less than 3. In this case, 3.5 is in the cumulative Poisson tables, and so all we have to do is look up the probability that y is less than or equal to 2, which is 0.3208. 4 decimal places because we are using the tables. The previous answer was 3137. That should have been 314 to 3 significant figures. And 3208, not a great deal of difference, a good approximation. Now let's look at another example. Suppose we have a whole lot of eggs packed in boxes. Occasionally you get a broken egg, but not that often. So let's assume that the probability that an egg is not broken is 0.94, so that most of the eggs we buy are going to be perfectly good. In a delivery of 100 eggs, find the probability of at least 90 eggs are not broken. Well, let's suppose that X is the number of unbroken eggs. Then X will be binomial 100, 0.94. Satisfies the conditions quite happily for a binomial distribution. Fixed number of trials, 100 eggs in a consignment. Fixed probability between trials, 0.94. Only two outcomes, broken or not broken. And if we assume we don't drop the same box of eggs, then there will be independence between trials. Well, 100.94, at least 90 eggs. That's 90, 91, 92, 93, 94, and so on. Rather tedious to work out. But in this case, 1 minus p is 1 minus 0.94, which is 0.06, and that is small. So we need to turn it round and think of now. We take y is the number of broken eggs. We take the opposite of x. Well, if the probability that an egg is not broken is 0.94, the probability that it is broken is 0.06. Still a reasonable amount to work out. If we look at the probability that x is greater than at least 90, so it's greater or equal to 90, then x could be 90, 91, 92, up to 100, and y could be 10, 9, 8, down to 0. So that will be the same as the probability that y is less than or equal to 10. Still too much to work out, so this time let's use an approximation. We know that y is binomial. The expected mean for y is n times the probability, which in this case is 0.06, and therefore that is 6. So let's approximate y twiddle b 100 0.06 with another letter w twiddle p0 6. So we're approximating our binomial distribution with n is 100, which is large, and the probability is 0.06, which is small, with a Poisson distribution with the same mean. We're now looking for the probability that x is greater than or equal to 90, which is the same as the probability that y is less than or equal to 10, which is approximately the same as the probability that w is less than or equal to 10. Now we can use the cumulative Poisson tables, and this just comes out to be 0.9574. Very much less work than doing all the work we would have to with the binomial You can't look the binomial up in the tables. 100 is far too big. So there are two examples for you using the Poisson as an approximation to the binomial. One where we had p was small and n large, and the second one where 1 minus p was small and n is large. Never, 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 never forget the second bit. 1 minus p small is also something where you can use the Poisson distribution as an approximation.